With us again, there we go. We have Slater Weinstock. We really appreciated the interview you gave us yesterday and some of the other things you shared. He's going to talk to us more about the nuts and bolts of his company, I think.
Or supply chain.
Supply chain, there you go.
Supply chain today. So yeah, I'm going to talk a little bit about the software supply chain, talk about what it is, talk about different attacks against it, talk about some frameworks for securing it, talking about some ways of securing it. So let's get started. So what really is the software supply chain? It's everything that goes into code, really. So it's the code, it's the binaries, it's the open source software that's being used. So talking about like that software bill of materials, this covers all of that, internal packages, build scripts. So all of the scripts that you run, the make files you use, how your software is packaged, scripts used to package it, the infrastructure the software runs on, who wrote the software, who reviewed the software, what licenses the software, what are known supported versions, when was it contributed, are there appropriate timestamps? All of that stuff is included in the supply chain. So it covers a huge amount of places. So as you can imagine, because it covers so many places, there are a lot of places to attack. So the two main components, or the two main areas rather, that the supply chain can be attacked in are either components under the company's control or components that are external to the company's control. For example, like open source software. So some types of attacks, I just listed some here. Dependency confusion, which we're going to talk a little bit about. Typo squatting, which you heard a little bit about with the Rust decimal versus Rust underscore decimal. Thank you. Developer accidents, so just accidentally doing something. Compromising an employee's account or otherwise injecting code into the company's private repository. This can happen a lot. Stealing code signing certificates, so then effectively you become the dev company, you can distribute software, or just directly attacking the build environment. So those are the main types of attacks that we can do. So we're going to talk a little bit about a few of them. So one is Trojan source. And so I'm sure a lot of you are familiar with Trojan source, right? Have you guys read the papers? Are you guys familiar with it? Okay, we got some people. So Trojan source is using Unicode, specifically bidirectional characters or bitty marks. And by using Unicode, you can do something really clever. So, end of the show, blah, blah, no, just for a second. So let's do a little bit of code review really quickly. Okay, can you guys read that? All right. Okay, so we have a really simple Go function here. And so what the Go function does is checks if you're an administrator. And obviously that's an comment, so that's not a big deal. If user equals ABC, return true, otherwise return false. We're gonna check, do check admin at DDD. I know I'm extremely clever with my naming. I'm really terrible with my naming, that was a joke. So if you're DDD, it should print you are an admin. So obviously this should not print you are an admin, right? Does everyone agree with that? Yeah. Okay, cool. So let's check. Let's just do a quick check. What happened? So what this actually exploits is what's called a right to left isolate. So let's actually take a look at the code in a little different form. So you might notice right here, there's a U2067. So that's an RLI character. So what that does is effectively, and if you remember this was over here, it effectively causes that to reverse. So it reads it right to left. So effectively, we return true right away. Would you have ever caught that if you were reading that code? Probably not. It looked like a comment. As far as you're concerned, I mean, remember, software is millions of lines of code. You might be doing code review on 100, 150 lines. I would have just looked at that prior to this and been like, oh, not a big deal. So this is an example of early return. And there's lots of different types of Trojan source that can happen. I'll show you another one. So this is a commenting out attack. So here I have a bunch of different characters. I have left-right overrides, I have isolates, I have PDIs. So the idea here is that this entire code segment, let me open it in a different way just so you can see it. So here, what you're running is you're doing a check if there's an admin, and if it's an admin, you're going to pronounce, yeah, you are an admin. So so is admin false? Is super admin false? So is admin should evaluate to, well, false. And if we're an admin, then we're going to print out you're an admin. And for some reason, this actually rendered correctly. Damn. Let me see if I have another one. 2 more seconds. Apologies. I checked the return light and checked the other one. Here we go. This is a good one. So if access level does not equal user, you're an admin. Obviously, the access level we're passing in as user, so obviously it shouldn't work. And if we open this up differently, you'll see that there's a bunch of characters in there. So if we run this, again, we're an admin, even though it did that check. So those are things that you may not see right away when you're doing code review. So that is Trojan source in a nutshell. Pop back over. So that kind of explains Trojan source. Now, SolarWinds, I'm sure most people are familiar with SolarWinds. What happened? Okay. So it targeted Orion. So Orion is a SolarWinds product. It's an IT performance monitoring system. IT performance monitoring means it's going to have some level of privileged access. And it's widely deployed to governments, deployed to multiple organizations. And what happened was the network was infiltrated. And as the network was infiltrated, the attackers very slowly started seeing if there were code injection vulnerabilities and if they could effectively inject it. Eventually, in February of 2020, Sunburst was introduced. Sunburst was a malware payload. It acted as a Trojan horse. And then code was signed because it was on SolarWinds build system, and it was deployed to 30,000 plus users. So at that point, code was executed in a bunch of different contexts over a bunch of different companies. Xcode Spy, this targeted iOS developers specifically. It took, it used tab bar interaction. It was a fork of that. And what effectively happens is you bring that into your application and it runs the malicious code. Effectively, Eggshell is a known Mac backdoor, if you will. So it effectively downloads that. It effectively downloads that, reaches out to a C2 server, and waits for commands. It technically acts like spyware. So the reason I say it's a first step is that you're not actually introducing anything into the supply chain. You're only monitoring what a developer is doing. But it can be used as a first step because, well, it's spyware. You can see what's happening. You can target other things later. So that's another example. Here's a node package manager example. So UA parser JS. What happens here is that a developer's account or developer's node package NPM account was taken over, and they took it over, disguising the takeover with email bombs. So what that is just spamming that email a bunch. So maybe you got a notification that, hey, your account was hacked. So what do? Well, I don't want you to see that notification, so I spam you a bunch so that goes way down and it takes you time to like look through your email if you even bother to look through your email. So after installation, what does this do? It effectively downloads a crypto miner and then runs it, and you're mining cryptocurrency for people. So, I mean, that's kind of awesome. Not saying, but kind of awesome here. So, dependency confusion. So this is an example I really like to talk about. And it's a little similar to typo squatting, and it's a little bit different. So typo squatting effectively takes advantage of people's common typos, and we'll talk a little bit more about that later. Here, on the other hand, what we have is we have an internal package repository system. These are commonly used in organizations. Why? Because they're trusted. An example of this is Artifactory, offered by JFrog, common in a lot of organizations. So here, all our internal packages are held. And so what happens? I do pip install -r requirements.txt. It goes out to internal package, fetches the most recent one, in this case 1.1.2. And then the internal package makes a call out to the Python package index. It downloads the rest of those packages following the requirements in the requirements.txt file. This returns, it caches it in the internal repository. It then distributes it out. So in this case, you would have the internal package class, numpy, and request 2.7. So nothing bad with this at all. There's no issue. But what if I create internal package 99 in the Python package index? So I love this. It's by design, right? It's not a bug, it's a feature. So what happens? Internal package repository, so Artifactory, in this case, it's like, hey, you know what? I see that there's a version 99 out there. So I'll get that for you. I'm going to be super helpful. Oh, thanks. You just introduced malware right into the system. So that is what happens. So super simple attack, just uploading a malicious package, Python package index. So a lot of people might say like, okay, yeah, but you need like internal package names. It's difficult. It requires knowledge. You can get this everywhere. You can scrape GitHubs. A lot of companies have public GitHubs that use their internal tools. So they'll have the names in there. Maybe they'll comment out. You can search JavaScript. For instance, you can look right at the console and you can look for require statements and you'll see little things that really indicate that it's an internal package. You can find things on Stack Overflow, developers posting like, hey, I don't know how this code segment works, and you're just like, oh, well, thanks for giving me your internal package chain. You can also just guess. Why? Because a lot of times companies will fork a public repository and then just append like, well, append this. Here's Yelp, for example. Those are 3 malicious packages. Those are 3 internal packages to Yelp too. Bunsen logger, Yelp JSM Pro, Yelp sitrep, and Yelp Bunsen logger. So those are all internal package names to Yelp. So it was actually exploited. A security engineer, hacker, but just kind of doing it for fun, demonstrated that he could take over a lot of companies. He took over Tesla, Apple, Yelp, Netflix, a few others. And all he did was scrape the internet, find a bunch of these, upload a bunch of malicious packages, and watch his payloads execute. Yeah.
So in your example, you're using the distinct package versions greater than or equal to a certain version. Can this just be avoided if you just use equals an exact version?
Yes, that's exactly. Hang on. Well, yeah. So we're going to talk about that, but that's exactly what you do is you can do what's called version pinning. And then there's another thing you can do to be a little bit more secure. So I will touch on that in just a second, but yes, exactly. So, well, where does this actually, why does dependency confusion actually get exploited? Well, a lot of times it's due to assumptions or confusion. For example, pip has a feature called extra index URL. You actually should never use extra index URL. You should use index URL. Why? Extra index URL says, hey, we're going to have the default behavior, but you can attach additional things. So what they'll do is they'll do extra index URL and they'll have their pointing to their internal package. Well, the default behavior is still go get the best version. Don't rely on one thing. So if you use index URL, it will only use what you tell it to. So that's an assumption, and also it's not a bug, it's a feature. So type of squatting, which we talked about a little bit before. So pip install request, that's going to install request. So what does type of squatting take advantage of? It takes advantage of common typos like requests, I can't pronounce some of these, but that's all it does. It takes advantage of of typos, and that can lead to arbitrary code execution, which is the holy grail among like hacking. You get arbitrary code execution, remote code execution. It's a lot of fun. It's a rush. You're up at 2 in the morning, you're like, oh, what can I do now? So, as he was talking about, so this was that attack with Rust Decimal. It's called Crate Depression, and all they did in essence is upload Rust Decimal instead of Rust underscore decimal. So once infected, or once a machine's infected, what does it do? It effectively determines if that machine is part of a CI pipeline by looking for the GitLab CI environment variable. If it is, it then reaches out and then downloads Poseidon payload. And just to be extra helpful, what it does is it marks as an executable and removes the quarantine bit so that it can effectively execute. After that, command and control server, also known as a C2 server, is set up, and then it waits for tasks. At this point, the C2 server actually isn't doing anything. So that doesn't mean that people aren't waiting to actually send tasks. It just means that for right now, tasks haven't been given. So what can I do with this? I can log your keyboard entries. I can record your screen. I can turn on your camera. I can pretty much do anything. I can take over your entire system. I can become a remote administrator on your system. So pretty big deal, especially if that's part of a CI pipeline. And what was really clever about this one is they added like friendly messages. And what I mean by friendly is something that like people who work in Rust would commonly see, like maybe a 503 network error code or something, and the corresponding message. So you don't really see any indication that, hey, there's something wrong. They have a whole list of IOC indicators of compromise that you can look for. Different versions. I believe in this one, there were 15 versions that were uploaded because the attackers were just trying to fine tune their attack a little bit, see what was going on. And eventually it got pulled and reported. So as you were saying, to mitigate against dependency confusion in Python, for example, don't use extra index. URL, also use version pinning. Version pinning means don't say greater than or equal to, say equal equal. Other things you can do too, which is even a little bit better, is use version hashing. So you actually add the hash, preferably SHA-256 hash, and then you do the pip install. Then it checks the hash. If the hash doesn't match, so in this case, I just have 2.1.0, that turned out horribly. This hash is for 2.1.2, and there's a little red error text there that says, hey, the hash doesn't match. This might mean that there's an issue with it. Yeah.
For MD5 and SHA-1, there's going to be more collisions, but why SHA-256?
SHA-256 is, I hesitate to say collision resistant stuff, but SHA-256 is just more optimal. You can do ED25519 as well. There's a bunch of different hashing algorithms or different algorithms you can use, but it's just a little bit better. You're less likely to have a collision. If you do have a collision, then it might think the package is the same, even though it's not. So here's another attack. So this is dependencies of dependencies. So in here, the dependency isn't targeted. Instead, well, I'll just go through it really quickly. So event stream, it's downloaded 2 million times a week. It's a hot package. A lot of people are using it. I can't believe I just said hot package, and I can't believe this part. Don't. No. So what the original author did is, said, hey, this guy wants to be a maintainer. Sure, you can be a maintainer, absolutely. So they gave maintain access to this person right here. And the new developer actually added dependency to what's called flat map stream. Now, flat map stream was not used at all. It was very low. It had like 1 commit, so not a very common package. Well, flat map stream actually had an injection payload in it, so it was an injection attack. And so what this maintainer or new maintainer did is bump the version, and bump the minor version rather, of event stream, add that dependency in there, let people download it for 3 to 5 days, and after that say, okay, let me cover my tracks and let me remove the flat map dependency, bump the major version of event stream, and then just let it go. So the malware in this case targeted Copay, which is a Bitcoin wallet app. And specifically and it was 5.0.2 to 5.1.0. So what it did is it put itself into the build. So the builders of Copay, or the source code Copay, during the build pipeline, they actually pulled in this dependency. So it targeted that. So this was distributed in all the versions. So what happened is a user would open up Copay and this would execute. What would it do? It would check if you had over 100 Bitcoin, over 1,000 Bitcoin cash. And if you did, it would take some of it and give it to itself. So what I have here is the developers actually talking about, in essence, saying, what the hell did you do? Like, why did you do this? I don't understand. So yeah, I don't know what to say. And he answered some of the questions here. So if you actually want to read the developer's response to this, this is just kind of talks about like the attack and everything like that. But yeah, so that brings up a good point. Well, this brings up two good points. One is vulnerable dependencies and vulnerable dependencies of dependencies. If you don't update, you could continually be vulnerable. Another thing is if you find a vulnerability in open source, make sure people know, don't just silently fix it and say, okay, cool, it's done, raise a security issue. And back again. So how do you prevent stuff like this? So there's a secure software development lifecycle, also called SDL. And the requirements for a secure SDL, you want to have clear requirements. They need to be defined up front. You want to perform threat modeling, establish all the design requirements, use cryptographic standards. So you have to understand what cryptographic primitives you're supposed to be using. Are you supposed to be using a stream cipher here if you're instead supposed to be using some other cipher? You need to keep an inventory of all third-party components that are used, and you need to perform dependency analysis or software composition analysis. You should only be using approved tools, performing stack analysis, so SAS, perform dynamic analysis, so DAS, and doing pen testing as well. So it's a multifaceted approach. So talking a little bit about that, threat modeling, the main steps are, you define security requirements, you diagram the application, you identify potential threats, you apply mitigations, and then you validate, and then you keep going in a circle over and over and over again. Like I said yesterday, security is a very, very iterative process. Why do this? It's freaking costly. It is extremely expensive when you built an application, you have paid all those developers, and you have made all these assumptions, and you have organized the architecture of this program in a certain way. That's a huge amount of money if you don't do this upfront legwork. So establishing design requirements. Important types of things are like authentication, RBAC, logging, cryptographic protocols. Why spend time establishing design requirements in crypto standards? This stuff's complicated. Two-factor authentication, what I talked about a little bit yesterday. If you're a system admin or something like that, you should not be using, especially for a big company, you should not be using text message. You should be using an authenticator app. It's a much more secure. Password complexity, don't allow a 6-digit password that's only alphabetical, all lowercase too. Actually have like, I don't know, 15 employ like LastPass, 1Password, sufficiently random, collision resistant hashing algorithms. So not using MD5 or SHA-1, for example. So what do I mean by SCA tooling? So SCA tooling, has anyone used things like NPM audit, Yarn audit, okay, we got some. So those are examples of like dependency analysis tools. Sneak is more of a software composition analysis. NPM also does a little bit of this. Yarn also does a little bit of this. There's Synopsys Black Duck, which is another SCA tool. But the real reason I've listed these is you want to kind of employ a lot of different ones. I have seen Sneak find 730 things in the NPM audit, find 20,000 things, for example. So each one has sort of their strength, each one has their weakness. Cross-referencing them gives you the greatest coverage. So, okay, you're developing a project, you ran this, and oh, yay, there's 20,000 findings, and you have 970 criticals. Yeah, this happens a lot. I've seen 20,000, I've seen 50,000, I've seen 100,000. Just because it identifies that you are using a vulnerable dependency does not mean you are using it in a vulnerable manner. So you can't just say, oh, it's identified, like we have to completely refactor it. You may have to look at what the CVE is. What was the actual exploit that rated that, and does our application touch that in any way or not? What does that mean? It means updating to the latest point release. That is the easiest way of narrowing down things. I think you can do like NPM audit fix. I think you can do yarn audit fix. For Sneak, there is a way of doing it. I've not used it. But updating, rerunning it, determine whether or not that fixed. Typically, that will cut down the number significantly. What if you still have like 14,000 or so? Assign a lot of people to go through them. Because truthfully, all it takes is one of those to exploit in your application, and you've been taken over. So, for example, in event stream, if you had just updates of a major release, you'd be completely safe. So tool use, things you have to consider, like what IDEs are being used, are appropriate plugins being used, what compiler and linker flags are being set in makefiles, for example. So I have a GCC example here using where, wall, wextra, stack protector, wsign conversion, and conversion. So wall just has a bunch of security checks. Wextra has even more. Where forces it to air out, which means you have to compile cleanly. Stack protector, stack protection is huge. Considering is the source code free of secrets. This one is something that a lot of people do okay. The history aspect, though, a lot of people don't. You have to remember, when you commit something to version control, I can go back and look at it and say, hey, thanks, you had some passwords in there, or hey, you had API keys or client secrets or API secrets. So really making sure both of those are clear. Developer documentation free of secrets. Developer documentation history free of secrets. Stack analysis tools are using things like SEML. Yes.
I was going to ask actually about the static analysis tools that you're just getting to. So like if you use Sonar Cube or Code Sonar or something similar, right? It doesn't really tell you too much about the dependencies. And so how does that really help with like supply chain? So
you do things like Sneak, yarn audit, or dependencies. So you have to use a bunch of different tooling. So SCA tooling, you also want to do stack analysis tooling. Stack analysis tooling would tell you things like, in your build pipeline, did you have Trojan source, for example? Did that get built? Did something fail? You could also have tests, so making sure you have appropriate unit tests, integration tests, end-to-end testing. Are there bad code practices? Are you using banned APIs, for example? So maybe you don't want to be using stir copy. Maybe you want to be using stern copy, for example. A lot of these types of things, when you're being a developer, you're not actually considering it. You're not thinking in that context.
There's also fuzzing and stuff.
Fuzzing as well, and we're going to talk a little bit about that. AFL, for example, American Fuzzy Lob is a great fuzzing program. A lot of really good stuff that you can get out of it, especially if you just like go for 3, 5, 10 days. So other areas to look at in the supply chain. Build reproducibility, code review. What is the release process like? How are build artifacts stored? How long are they retained? Is access revocation in place? How long does the developer session stay active? Is the build automated? So, oh, wow, I'm talking fast. So what I want to get to is Salsa. So have any of you guys heard of Salsa? Okay. So what it stands for is supply chain levels for software artifacts. It was actually developed by Google, and it's a way of securing the supply chain. So it consists of 4 levels. And ultimately, the levels boil down to, in level 1, you have to have an automated build, and you have to have provenance to build. In level 2, the source and build have to be hosted, and the provenance has to be signed. Level 3, security controls are required on the host, and the provenance cannot be falsifiable. And on level 4, you need to have two-person reviews. Your build needs to operate in a hermetic environment. And so really the 4 components come down to the source requirements, the build requirements, the provenance requirements, and then the common supply chain requirements, common build requirements. So for instance, in the source requirements, so each of these build upon each other, well, except in case level 1, level 2. So in level 1, you don't have to use version control. You should, but you don't have to. To get to SLSA level 2, though, you need to be using version control. In level 3, your history needs to be verifiable. That means anyone that committed has to be strongly authenticated. It means they have to be logging in with 2FA, for example. Has to have a timestamp. The source code and all the revision history must last for at least 18 months. That cannot be overrode unless you have 2-party approval by the admins. And then level 4, you need to retain that history indefinitely. 2-person review required for every change in the history. They must be different people, and each must strongly authenticate. So why would it matter to retain the history for so long? Well, A, if you ever want to go back and look at features or anything or get blamed. But 2, we talked a little bit about this with SolarWinds, even though they're part of the build system. Sometimes a person will just try something, wait a month, wait 2 months, try another thing and see what they can start doing and if they will get detected or not. If you only keep it for 6 months, you may not know when the initial hack even started. And if you don't know when that started, it becomes a lot harder to figure out everything pretty much. So in build requirements, for example, in level 1, it needs to be scripted, so you need to be using a makefile. In level 2, you need to be running it as a service, so you can do a build in GitHub Actions. There's other ways of doing it. Google Cloud has a service for doing that. In level 3, the build definition and the configuration files have to be stored in version control, and the code has to be built using those by the service. So everything has to be run there. Build has to be performed in an ephemeral environment that's only used for the build. Why? Because residual artifacts might linger around, so it needs to be clean. It needs to be, in essence, in a clean room. And the build service has to be isolated, so nothing else can be influenced, or nothing else can influence or be influenced by the build. And then level 4, you have a lot that has to be achieved. So touching on the last few points, because the other ones are all the same, the build must be parameterless. So everything has to be defined. No developer can be putting anything into it. Build has to be hermetic, which means everything has to use immutable references. All artifacts have to come from a trusted control plane in the organization. And artifact integrity has to be verified at each level. And then the build has to be, or doesn't have to be, should be reproducible. And then provenance. So again, in level 1, you have to make it available to consumers. The consumer has to accept the format that you give them to. In level 2, authenticity and integrity has to be verifiable by the consumer. And the data has to come from the build service, not you saying, hey, I promise. In the last talk, there's a lot of talk about trust. This is trying to remove that aspect of trust on the developer side and saying, like, I want proof that the build has done this stuff. In level 3, it has to be non-falsifiable. That means it has to be signed. There has to be a signing key. It has to be stored in a secure key management system. Has to be generated in the trusted control plane. That's where the provenance has to be generated. And then level 4, it needs to contain every single thing about all the dependencies, the state of the machine, anything that touched it. It has to include, or has to be included rather. So the content requirements of provenance. So in level 1, the alpha artifacts, who performed the build, who created the provenance, all the build instructions at a very high level that were followed. So that could be something like, hey, execute makefile in .wax/make. Makefile, for example. In level 3, identifies the entry points of the build definitions. All the build parameters have to be controlled, or all build parameters that can be controlled by a user are identified in it. And so an example provenance at level 3 is right here. So you can see that's what you cannot see. Excuse me, I apologize. So right here, so there is a lot of information here. And this is the standard format that you're probably going to be in. But you can see that it identifies a lot of steps, a lot of things that are included in it, SHA hashes, what environment was ran on. So yeah, they are using SHA-1. But that's an example of like how detailed these configuration files actually have to be, or should be rather. And then level 4, all transitive dependencies have to be included, and there's one parameter that's controlled by the user, and that's whether or not the build is reproducible. And then the common requirements. So these aren't really required in levels 1 through 3. They're all recommended, of course, but in level 4, like all systems have to routinely undergo vulnerability checks. They need to be patched. They need to be secure boot has to be enabled. There has to be appropriate transport security. Access, so you shouldn't be touching them unless it's absolutely needed. If it's needed, it has to be logged very thoroughly. Requires multi-party approval by 2 system administrators. And super users, yeah, there only should be a small number of them. Not every single person who's operating in an environment should be giving admin privileges. That's just a recipe for disaster. So I ran through that. That's all I have. The rest of this, if you want to see where I got anything from, you can totally go to any of these slides that has all the stuff on it. These slides will be uploaded, so you will have access to all of that. But that is all I have. Any questions on anything? And sorry for running through that. Yes.
It's a lot to take in.
Yeah, so there's kind of this like dive deep phenomenon. You're kind of like throwing with the sharks in a way. No, so there is a level of like you do have to dive deep. Cybersecurity is a whole other field that has a bunch of rules, regulations, policies, techniques, tools that are used, lingo, all of that stuff. So was I interested in hacking? Yes, I mean, we all played Watch Dogs. Come on, I mean, no, that was a terrible game. Yeah, no, I thought hacking was really cool. I thought the idea of hacking was really cool. So yes, I was interested in cybersecurity. Did I know all of this stuff when I first started? Absolutely not. I learned a lot of it over months and months and months of spending time outside of work, reading, researching, talking with my colleagues, talking with my bosses, and being like, hey, you know, like, so one of my bosses did a bunch of initial research into Unicode and presented at Google back when the Unicode compusables were just coming out. So that's the idea of like homoglyphs, for example, characters that look like the same character, but they're not. So a Cyrillic E, for example. So learning a bunch of that stuff. So it took a long time to get up to speed on it. And I mean, I have a permanent beginner's mindset because you're constantly learning new things. And just because something was best practice doesn't mean next year it will still be best practice. It may be outdated at that point. Any other questions?
Just a comment, going back to that event stream
Yes.
thing you mentioned. I went to that link you had on the slide and I kind of read through the issue there and the comments thread.
Mm-hmm.
It's actually kind of funny. And at one point, someone asks the user Dominic Farr, who's decided it is, they said, "Why did you give Right9 control? You know, why did you give this module to them?" And he says, "Well, he emailed me and said he wanted to maintain the module, so I gave it to him."
Yeah, and he didn't want to maintain it anymore. He was kind of done with it. And so, I mean, that's a level of trust, and ouch. Double ouch, actually, because it got used by a lot of people too. But I mean, this is where it's kind of like that aspect that Anthony was talking about previously. Like having a bill of materials, understanding where your dependencies come from as you become more reliant on it. There's a whole chain that has to be validated. It's not as easy as like, hey, NPM, let me install it. We're good to go. Even though I know when I was in school and stuff, I totally did that. I was like, hey, it works, done. Yeah, no, it's crazy. Any other questions? Awesome.
Thank you.
Yes.